The reported detection comes from an ancient mudstone, fine-grained sedimentary rock. Fine-grained sedimentary environments can function like vaults. On Earth, certain clays and fine sediments are known to absorb and protect organic material, reducing exposure to destructive chemistry. If Mars preserved organics anywhere, buried fine-grained sedimentary rocks are among the smartest places to look. So the setting fits the hypothesis. Not organics everywhere, but organics can survive in specific protective contexts. And that distinction matters because it turns exploration from a random search into targeted sampling. It also reframes a big misconception. The most important question is not, did Mars ever have organics? The more revealing question is, where on Mars can organics survive long enough to be informative? That's why this is meaningful even without any talk of biology. It's a map marker that says, these rocks can hold memory. Now, what does this mean scientifically? There are three levels of meaning. First, chemical meaning. The Martian organic inventory is not limited to tiny fragments. The detectable signal extends into longer-chain carbon chemistry, which suggests either formation or preservation, likely both, of more molecularly complex organics than previously confirmed in situ. Second, planetary meaning. It strengthens the idea that Mars has preservation niches, geological environments that act as long-term containers of chemical information. That changes search strategy. It pushes exploration toward the right strata, the right mineralogy, and the right burial history. It also makes the where question just as important as the what. Third, astrobiological meaning. This is where people want to sprint and where we have to slow down. These molecules are not biomarkers by themselves. Organic molecules can be produced without life, by geochemistry, hydrothermal reactions, radiation-driven chemistry, and delivery by meteorites and interplanetary dust. Carbon chemistry is not a signature of biology. It's a feature of chemistry. So the honest statement is this: the discovery increases scientific motivation and sharpens target selection, but it does not prove life ever existed on Mars. If you want to argue for biology, you need lines of evidence that are difficult to explain abiotically. You want patterns in molecular distributions, contextual mineral associations, and ideally isotopic signatures, because isotopes can carry a fingerprint of formation pathways. Here's a simple way to think about that without getting lost. A molecule is a word, a pattern is a sentence, an isotopic signature is the accent. One word tells you almost nothing. A sentence narrows meaning. The accent can hint at origin. You also want consistency across multiple samples, not a single dramatic outlier. Science doesn't crown a winner from one data point. Science looks for repeatable structure in the noise. And here we hit the hard limitation of Mars science. An onboard rover lab is extraordinary, but it's not a full Earth laboratory. Precision, repeatability, and the range of analytical techniques are fundamentally constrained by power, mass, and environment. Which is why the story doesn't end with, "We found organics." It points forward to, what would it take to know where they came from? That question naturally leads to the idea of larger-scale investigation. More drilling depth, more diverse sites, better shielding from radiation during analysis, and, most importantly, more samples. This is where NASA and SpaceX both naturally enter the same conversation, without turning the science into an advertisement. NASA represents the disciplined scientific pipeline, incremental missions, careful instrumentation, cautious claims, and long-term strategy. Curiosity is part of that pipeline, turning a planet into a data set, not a rumor. SpaceX represents the possibility of a different scale of logistics. If heavy-lift, high-cadence Mars transport ever becomes real, it changes what can be done on the surface. More mass, more power, more shielding, deeper drilling capability, more robust labs, more samples, and more repeated measurements across many sites. It also means faster iteration, learning, adapting, and redeploying hardware based on results rather than waiting a decade between opportunities. Because the true enemy of certainty is not mystery, it's scarcity. Scarcity of samples, scarcity of context, scarcity of repeatability. Mars doesn't answer with headlines. Mars answers with rock. Picture a world that looks simple from a distance. Red dust, cold stone, thin air, silence. But underneath is a chemical archive that's been exposed to radiation and oxidizing chemistry for billions of years. Anything fragile should be erased, especially organic molecules. And that's why one recent claim hit so hard. NASA reported that its Curiosity rover detected the largest organic molecules found on Mars so far. That line sounds like an ending. It isn't. It's the start of a much more serious question. What exactly did they detect? How did they detect it? Why does it matter? What does it not prove? And what would it take to turn interesting chemistry into a real conclusion about Mars's past? If you want science without hype, clear, honest, and still cinematic, subscribe to the channel. And if this kind of deep breakdown is your thing, hit like. It tells the algorithm this is worth showing to more people who care about real evidence. Now let's do this the right way. First, we need to remove a common misunderstanding. Chemically speaking, organic refers to carbon-based substances, distinct from anything derived from life. Carbon chemistry is pervasive, originating from geological processes, extraterrestrial sources, and non-living reactions. Thus, finding organics on Mars is a statement about carbon chemistry, not a declaration of life. But the crucial word here isn't organic, it's largest. NASA's focus is on the detection of comparatively long-chain carbon molecules, hydrocarbons in the C10 to C12 range, retrieved from ancient sedimentary rock. On Earth, these are ordinary. On Mars, within a radiation-ravaged archive and analyzed by an onboard instrument, they are remarkable. Why? Because length equates to fragility. A longer carbon chain is akin to a longer string. More points of potential breakage, more avenues for radiation to dismantle it, and more chances for oxidizing agents to corrode it. Mars is unforgiving to organic matter. Its surface is a destructive force. Over vast stretches of time, complex molecules should naturally decompose into simpler fragments. So when you detect longer chains, you're not just learning that carbon exists. You're learning that something about the environment, where the sample formed, how it was buried, what minerals hosted it, allowed chemical information to survive. That's not a minor detail. That's the difference between noise and a readable signal. That's the first major takeaway. Mars can preserve more complex organic signatures than many people intuitively expect. But we have to be precise about what detected means. Curiosity doesn't see molecules the way a microscope sees cells. It runs analytical chemistry in a constrained, harsh environment inside a rover. One of its key instruments is SAM, sample analysis at Mars. At a high level, SAM heats the sample and analyzes the gases and fragments released during heating using techniques like gas chromatography and mass spectrometry. That method is powerful, but it comes with an important nuance. Heating can both reveal compounds and transform them. Some of the molecules you detect after heating may not be the exact original molecules that sat in the rock for billions of years. They can be products of thermal breakdown, pieces produced when larger, more complex precursor molecules crack apart under heat. In other words, you may be seeing the shadow of something larger, not the intact original object. This matters because one scientific interpretation is that the detected hydrocarbons could be derived from larger precursor organics, possibly long-chain carboxylic acids, rather than being the pristine original molecules. If that's true, then the headline understates the real implication. The source chemistry could have been more complex than what the instrument directly reports, and that's a key scientific mindset shift. In planetary chemistry, you rarely get a clean photograph. You get clues. You reconstruct the most likely story from the total evidence. What compounds appear, in what ratios and what rock type, alongside what minerals, under what thermal conditions. That is not a flaw in the result. It's how field chemistry works. You collect signals, you evaluate multiple plausible pathways, and you test which explanations best fit the full context, geology, mineralogy, and the full pattern of compounds, not just one peak on a graph. And that brings us to the next critical point, where the sample came from. Geology isn't background scenery here. It's half the answer. One rock can hint, 100 rocks can convince. And the Discovery Curiosity reported is basically a message from the archive. Chemical pages are still readable in the right places. The question is whether we'll bring enough tools and enough patience to read the rest. Now let's sharpen the conclusion. NASA did not say we found life. NASA said we detected longer-chain organic molecules in an ancient sedimentary rock, expanding the confirmed molecular complexity of Martian organics found in situ. The meaning is not a trophy. The meaning is a strategy shift. It tells us that Mars can preserve complex organic signals. It tells us where preservation may be best. And it tells us the next question is no longer, are organics present? But what is the origin story of this chemistry, and can we test it in a way that survives alternative explanations? Because the real divide isn't between believers and skeptics. It's between stories and evidence. And this is evidence. Quiet, technical, and powerful. Not a final answer. A surviving page. Mars is still not shouting, but it is speaking. And now we know how to listen.